Okay, let's get started. Can people on Zoom hear us? Okay, I see a thumbs up. Welcome to the Photometric Redshift session. Hope you have been enjoying the week so far. The chair of this session is Eric Charles, but he can't make it in person today, so I will be the standing chair. Just a reminder of code of conduct and respect each other. And also a reminder for virtual participants to stay muted when they're not speaking. And you can find the Slack channel for asking questions in the Slack space for Rubin 2026. And today we have a pretty full agenda. So first, Sam Schmidt will give us an overview of Rubin Photo Z. Julia Schwen will give an update about LSST Photo Z server, including status, new capability, application for DP2. I am TQ, so I'll give a DP2 photometric redshift product overview. And Josue and Eric will talk about the Photo Z data challenge, and Justin Miles will talk about N of Z data challenge. So let's start with Sam.
All right, I'll go very quick because I noticed that we have over 60 slides, and I think that doesn't include Julia's slides. So as a very, very brief introduction for what we're doing, just as a reminder, our ultimate goal is to try and predict the redshift of billions of objects in LSST based on a very small number of observables, say the 6 LSST photometric bands and their uncertainties. Just as a quick primer, most of our information in Photo Z, the reason Photo Z's work, is that we have these sort of top hat filter curves, and we have broadband features in galaxies like the Lyman break and the Balmer break. As those features pass through the bands, the color, you can see I have a plot here of U minus G, G minus R, I minus C, Z minus Y, as a function of redshift. As the break goes through, the color increases and decreases, and this extrusion out of the sort of ball of color in the plane gives you sort of a rough idea of the redshift. You can see a color plot here, color coded by redshift, and galaxies sort of spiral in color space. And if you can isolate a galaxy in color space, you can get a pretty good idea, a rough idea of the redshift of that object. There are some problems with that. You can see areas where there are blue and red points at around redshift 0.2 and 2 right next to each other. You get degeneracies. You can see in the lower right of the Photo Z versus Spec Z plot in the lower left there, you have a little blob of degeneracy where, given the 6 colors that we have, or the 5 colors, 6 bands of LSST, you can't actually distinguish those 2 redshifts, and you have bimodal solutions to the redshifts. So that's roughly what we're trying to do. It's not an easy problem. It's not a solved problem. Otherwise, we wouldn't have a session here. And it's extra hard because we have deeper data than any survey has ever had before now. So in this session, we're going to talk about some of the things that are still concerns about redshifts. The biggest one, I think, is training set incompleteness. This is an old plot. This is from Masters et al. 2015. This is a self-organized map showing the occupation of sort of color space as a representation of all the color space of galaxies we expect to observe. The gray are areas where we have 0 spectroscopic redshifts, so we have no idea what the redshifts of objects for those colors are. Again, this is 10 years old, so in the meantime, we filled in some of this color space. But there are areas of galaxy space, the SEDs of galaxies with certain colors, where we just don't know the redshifts of those galaxies for sure. We have ideas based on models and things, but we don't know for sure, and that makes them hard to calibrate. The other thing, photometric and photometric redshifts, it should be pretty obvious that we're very dependent on the photometry. We have a brand new telescope with a new design, new data management software. We're still checking what exact photometry we should be using for our Photo Zs. Are we using C model magnitudes? Are we using Hop magnitudes? Are we using some aperture magnitude? We want a consistent estimate of flux or magnitude as a function of various observables. You don't want to be dependent on seeing. You don't want to be dependent on the air mass that you're at or other observable effects. You want to be uniform across the sky. And for DP2, we're a little less uniform than we expect to be even for DR1. So we're going to talk about DP2 Photo Z's TQ will in this session. It will be a little extra concern because it's a little less uniform than some of our other data sets. Computation and storage is another issue. We're doing estimating redshifts for billions of galaxies. That really is not so easy for some of our algorithms. Some of our algorithms run in milliseconds per object, and it's all fine. It's actually not a huge computational version. Others take like a second per object, and that is less scalable. And so that is something we have to worry about. Some science collaborations care about things like physical parameter estimates. That is an even harder problem if you're trying to estimate. It's already, we've got 6 numbers we're trying to get a redshift. That's already amazing that works. If you're trying to also do a bivariate estimate of galaxy properties and redshift from 6 numbers, it's hard, and it's also computationally intensive, and how you store a 2 or 3 dimensional information in a finite number of floats is also difficult. So that is something we also have to tackle for specific science cases. To answer this, we've in the DESC, Dark Energy Science Collaboration Group, developed a software package called RAIL, Redshift Assessment Infrastructure Layers, to make it easy to quantitatively compare different PhotoZ codes against each other. We have a bunch of metrics. We have a suite of tools, and it can be run anywhere from notebook all the way up to at scale. We will actually use the software to run our PhotoZs. And so we can use this, and we will use it for things like a data challenge that we'll describe to compare codes, see where we're doing well, where we're not doing well, which codes take a long time, which codes can store the information needed, and hopefully give us everything we need to generate PhotoZs. And this is likely the software that's going to be used to actually populate tables that are output by the project. They will be some subset of RAIL algorithms that work as best as we can. The other thing to think about is when people say PhotoZ, there's not like one algorithm that works best for everyone. It's going to be a bit science case dependent. Our task is to try and come up with a sort of general use PhotoZ that is the most widely useful to people, and we need some feedback on what is needed and what that is that we can populate the tables in the Rubin tables for. And so I'm already running a little long, so I will stop there and hand over. Is Julia there? Yes.
Good morning. Second. Okay, can people on Zoom see my screen? Yeah, thank you. Okay, good morning. I thought that it's less boring if I show you the PZ server demo live a little bit. So I'd like to give you a little bit of context. And the PZ server is one of the web applications of the Brazilian IDEC user interface. So the Brazilian IDEC has not adopted the Rubin Science platform. We have our own Jupyter Hub and image visualization tools and a couple of science-driven applications as well. And just let me show you this web page for the Brazilian IDEC user interface. And here we have the PZ servers. So the PZ server is open to all Rubin community. So if you are a data rights holder and you have an RSP account, you can just log in using your RSP account without any extra registration needed. So you select your identity provider. In my case, it's Linear. And this is the authorization page connected to the Rubin Science platform authorization system. And then we go to the PZ server homepage after a little while, where we have these 3 cards. First is for the Rubin Observatory PZ data products, the official data products. That for now, it's an empty page because the official data products are going to be delivered starting with GL1. So The second one is for user-generated data products. It's your data product. We encourage you to upload your data products there to have it safe and backed up and easy to share with your colleagues from the collaboration. You can sort data products. You can filter, for instance, by release. We already have some DP2 data products in there, and you can filter by product type, for instance. And then you can upload your own data products in here. So I have one upload left. You can just discard. So for the upload, you have 4 steps where you provide basic information about your data, and you upload the files. You do a column association to let the system know which columns are redshifts and coordinates, and then you check the information and confirm your upload. So, and the third one is for the PZ server pipelines. There are 2 pipelines in there. They are both cross-matching pipelines that uses LSDB as the backend. The first one is to combine multiple reference Redshift catalogs to a single one, to a single compilation. So you have to select, choose a name for your product, select one or more input catalogs in here, and there is a couple of configuration choices. So you have options to stack all the data from all the catalogs together without resolving duplicates. You can resolve duplicates, cross-match all to identify which measurements are for the same galaxies and add this information as an extra column, or you can remove all the duplicates and select only one measurement per galaxy. So this is the current possibilities. And the second one is the training set maker, also a cross-matching pipeline. And this time you select just one reference Redshift catalog that can be an individual one or a compilation, and one LSST release. So it will match your catalog with Rubin object, LSST object catalog. So for now, we already have DP2 there because of the release of the heads collections, object collection released by Link. So for now, we have only the PSF magnitudes, but when we receive the complete object catalog, it will be more flexible for you to choose which kind of fluxes or magnitudes you want to add to your training set. And it's also super flexible for the format of the data, and we have support for head collections in all steps of the PZ server for download and upload, and also for the outputs of the pipeline. So going back to the IDEC page, I would like to show you 2 content pages that we keep. One is the documentation, where we have the user guides for all our applications, so you can switch to English and find here at Science Platform the LSST PhotoZ server. So there is an extensive documentation on how to use it and how to take advantage of all features. I would like to show that we have a Python library, so you can connect via an API and do everything you do from the website. You can also do from Python code. So there is an authentication token that you get from the site, and then we can just pip install PZ server and import PZ server and do whatever stuff you like to do with the server. And also there are pages for teaching you how to use the 2 pipelines. And also we have this another content page with data. Because we don't have yet official data products, so we have preliminary data products that are let available by the PZ server team. Those data products that were created in the context of the community, the commissioning team, and they are here available. Let's switch to English. And under science products, LSST PhotoZ server, we already have some data products related to DP2 and also those that for DP1. DP1, we have those data products that are described in the seed contact note 154. And for the DP2, we have already the data products related to a Rubin tech note that it's been in preparation. It's RTN124. And TQ is going to give you details about these data products. And we also keep a list of external data sets is the reference redshift catalog, mostly spectroscopic, but also photometric, high resolution photometric, and a list that data products that we have here available on the PZ server with links to the papers. And for instance, let me show one. Each data product has its own page with details where you can download, you can explore. There is a table preview here with the 10 first rows of the catalog. And we also provide a quick characterization notebook for you to take a look on the characteristics of the data. For instance, here for the slow data release 17, spatial distribution, and a couple of plots like a redshift distribution and so on. So we can go back and I can keep all these slides. Okay, so about these data products that were produced in the context of the Rubin TechNote 124, the preliminary data products for DP2, we use the compilation of the spectroscopic data that we found in DP2 footprint, and this is the list and the link to the 3 data products. We provide 3 flavors of this compilation of reference redshift. One is the complete, is the total measurements that we have up to the date. There is about 43 million redshifts. And the second one is a clean version, already resolved for duplicates and only with quality flags 3 and 4. And the last one is removing DESI from the compilation before the duplication, the resolving duplication step. So you can have the same galaxies that we have for DESI sample, but with measurements from other surveys. So after cross-matching this with DP2 object catalog, we have this training sets, the raw training sets, and also the curated training sets that you is going to talk about. And this is the 2 distributions of matched catalog, the compilation on the left side and for DESI DR1 on the right side. And for the compilation, this is the individual contribution from the different surveys after matching. So on the left side, we can see the surveys that contributed with the most numerous catalogs after matching. So I have been presented the PZ server in previous Rubin community workshops. So the news since last time is that now we have the authorization and authentication system fully operational and integrated to the Rubin Science Platform system. The 2 pipelines are development are completed. What we thought, what we planned in the initial design document is already done. So future new features will be driven by your requests. Please let us know how can we improve that to help you do your science with these tools. We already have this cycle of spec decompilation in practice. The idea is to continue gathering data from public releases of spectroscopic surveys until DR11. So we keep gathering data, standardizing and homogenizing the formats, and updating the compilation. We have already 38 external products with more than 50 surveys because there are compilations in there. So sometimes we do compilations of compilations. And we also, the news is that, one news is that we have already had formats support in all steps of the PZ server. So for the future, we are working on the real-time value-added catalog creation service, and we are going to integrate that to the training set maker, so it will be more flexible for you to choose which columns and transform columns to create your customized training sets. We also are planning to enhance the user experience by when you do PZ server, import PZ server and you already are logged in Rubin Science Platform, we are trying to figure out a way to detect that you are already logged in and do not ask you for an authentication token. And we are also going to ask for RSP team if they can put the PZ server in the library in the default environment for RSP now that the library is more mature, we are more comfortable to ask this. And also we are going to provide the P2 full PDFs catalogs, and we are still thinking on what is the best way to provide this. It should be via LSTB at Linea or via tap surface or both. It's to be defined. So before finishing, I'd like to thank to our team, is the three of us. Luigi Silva is data scientist, it has a cosmology background, and Cristiano Civulani, full stack developer that is in the project since the very beginning. And also thank our sponsors for the funding support. So if you need support, please reach out to us at helpdesk@linea.org.br. And to summary, the PZ server is a collaborative environment for you to create and share PZ data products. The PZ server extends the RSP capabilities for PhotoZ related science. It's offered as software and data curation services to Ruby as part of the Brazilian in-kind contribution program. It is hosted in the Brazilian IDEC, and it's open to the whole LSST community, so no registration required. Use your RSP credentials. And the PZ server team provides curated and documented data products, including those created by the commissioning team as in the PhotoZ science unit. So PZ server and other IDEC applications are available as beta versions. So please use it and tell us how to improve it. Thank you.
Is there a mic for the Zoom? Thank you, Julie. This is amazing. And it's just three of you? Did all of this?
And also that guy is responsible for the infrastructure.
Okay.
And we are the whole Brazilian team is welcome people. Yeah.
This-
For the PZ server specifically, it's here.
Okay, so this is really amazing. I did not know that there was this much. Yes. So I'm in my brain. I'm thinking of this use case with you have all of these. Can I actually, for example, choose a small patch of sky, and then put it in here in some sort of query tool and say, please tell me where all the spectroscopic and all the photometric redshifts done by all the different people that have loaded up into your system, and tell me what they all are, so I can look at the objects in this patch of sky and see what everybody did and whether or not they all agree with one another? Is there a functionality of that nature?
Not now, but totally feasible. If you have your like object catalog that is already clipped in your sky area, you can upload it and use it to cross-matching, use the cross-matching tool. For now, the cross-matching tool is not that flexible. I told about this science-ready catalog, value-added catalogs that we are working on. And when it's ready, so your the answer for your question will be yes in near future.
That's amazing. Again, thank you so much.
Appreciate it.
Ismail, do you want to speak up about your question?
Okay, so I'm asking if these catalogs can be used in the brokers. I mean, they're not completely public, and the brokers produce public information.
I don't get it. Could you repeat, please?
What I mean is, if these catalogs can be used by the brokers.
Yes, they are. The external data sets are all public, and those that use LSSP data should respect the data policy. So if you are data right holders, yes. Sorry, if you have data rights, yes. But the reference catalogs are public.
Okay, thanks.
Thanks a lot. It's great to see you made a ton of progress. It's really cool. I think we could sort of see how things are going, but can you just give us a brief summary of your vision for DR1? So what data products you'll be looking to host at the Brazilian IDAC and serving through the PZ server, and how we should think about what you're providing in that DR1 context.
Okay, so first, a compilation of reference redshifts that is complete at the time, including all data that is in Rubin, all the data available that is inside the LSST footprint at the time for DR1. Then the result of the cross-matching of these with Rubin photometry. So what we call the raw training set, because the curated training set will be strongly dependent on the science case. So the idea is that people will have tools to do their own customized training sets, but we are going to provide one raw result of the cross-matching. And also the result of PhotoZ estimates. It's also part of the in-kind contribution that we provide a second one or third one, different from the one that is going to be provided by the data management, to be an alternative photometric redshift estimate for the whole objects catalog. And that one will probably not be through PG server because it's designed to be for lightweight data products. So it probably is going to deliver that as LSDB, heads collections, and or TAP service as well.
And that would sit alongside the Rubin-based product.
Yeah, the initial plan is that we deliver to be integrated as they call federated data products. So the idea is that we process that in the Brazilian IDAC and then upload back to USDF so they can be easy joinable with the main table in the Rubin Science platform, besides our local copy in the Brazilian IDAC. But this process of uploading back is not yet well defined how it's going to work.
Okay, let's give a hand to Julia. Okay, hi, I'm TQ, and sorry, I just messed up my shirt. So I'll be briefly talk about the photometric redshift production for data preview 2 on behalf of the PhotoZ science unit in Rubin Observatory. So this is the work heavily standing on the shoulder of the PZ server team's work for curating the training set and test set of the DP2. So we get the full reference cross-match with DP2 from the PZ server, and basically we do a downsampling by binning these redshifts in redshift IBAN 2D binning. And the point of this is to reduce the number of galaxies that are concentrated in a certain magnitude or redshift because of some of these reference catalog being concentrated, like DESI and SDSS and or 2MAS and 6EF. And the outcome of this downsampling is that we'll have a much flatter training set for PhotoZ in the magnitude redshift space. And as the plot on the left shows, the blue is the total cross-match, about 1.4 million objects before the downsampling, and after this downsampling process, it's flattened, and gets down to 500,000. And same for redshift space as well. And you can see that the composite of this training set by survey, and the majority of these, including high and low redshift, is coming from Cosmos 2020, but also a lot of them are coming from the Cosmos spectroscopic sample and DESI sample, etc. So for the test set, to correctly reflect the performance of our PhotoZ on the DP2 sample, we want a test set that closely reflects the magnitude color space of the DP2 sample. So the strategy to get that is we take 20% of the reserve galaxy from the cross match. We train a self-organizing map on the 1% of DP2 galaxy to get the magnitude color distribution, and we downsample the 20% to match the population of I-band and color distribution. And let me show a plot of what I mean here. So on the right-hand side, this is showing the redshift magnitude color distribution of the following samples. The green sample is the DP2 population, and you can see the downsampled test set, which is in orange, basically closely follow the DP2 population. So by doing this, we know that if by evaluating our PhotoZ on these reference samples, we get a better outcome of what the actual performance is for our PhotoZ. And you can also see the blue training sample that covers a wider range in redshift, magnitude, and color, and that's what we want to have for training a machine learning model. For DP2, we currently train and test our algorithm on the following algorithms in Rail. And there are 7, but you'll see 6 panel of plots. The reason the FAR is currently not involved is because the runtime for production is too long for LaFAR. So in our validation, we are only testing the 6 algorithms, including BPZ as a template fitting algorithm and the 5 machine learning algorithms that also appeared in the DP1 PhotoZ. And you can find the configuration of these algorithms in our Rail project config repo under DP2. And let's jump into performance of PhotoZ. So this is a standard plot of Z best versus Z reference for the 6 algorithms. And you can see that as what we found in DP1 as well, the FlexiBoost achieved the best scattering metric, while in this time PPZ actually does slightly better than FlexiBoost in terms of outlier rate. But overall, all 6 algorithms performs relatively well, and we decided to run production for all of them. And this is showing the delta Z as a function of I-band magnitude, and as you can see, that the DP2 depths is roughly 23 to 25, depending on where you're looking at. So the scatter metric really start to go up after you reach 24. So for the DP2 production, we're for DP2 we're running 6 rail algorithm in the so-called pipe task, which is in the DM stack language. So the KNN and DPZ are wrapped in the MIAS PhotoZ base package, and the other algorithm are in a different package. And this is the first time we run these new pipelines, and we're also getting an estimate of the runtime. And so for running the 6 algorithm, we spend about 1 to 2 days on 300 cores on the S3DF batch. And so if you're interested in rerunning PhotoZ, this is what you want to expect. This because we're running the code in the DM framework, everything is ingested into Butler, and we later have a conversion stage to get them out of the Butler and ingest into LSDB. I just want to mention one key caveat for this data set before you guys jump in and use it. Because the inhomogeneity of DP2, the mean or the redshift distribution really depends on where you're looking at. So for a deeper part of the footprint, you would expect a higher mean redshift. And this is so in this plot, I'm showing the mean Z-best of FlexiBoost across the full DP2 footprint. And you can see at the galactic plane, it's heavily extinct. So there's not much galaxy, and please don't do extragalactic science at the galactic center. But even at the wide field, at the higher galactic latitude part, you can really see a dependency of the mean redshift on the depth if you overlay the depth map, and you can see the deep drilling field have a higher mean redshift. So go with precaution. I also want to note that some of the DP2 footprint has only 6-band coverage. So we actually trained 2 sets of model, so that there's a 6-band model and the 4-band model. And for footprint that are only covered by 4-band GRIZ, we'll use this 4-band model. So these photos are actually generated by different models, depends on their band coverage. Okay, so this is my last slide, and probably what you care about, getting the data. So currently the DP2 Photo Z is available in LSDB HATS format. We curate the PDF output into 4 point estimates, the mode, mean, median, and the best, and also the 1 and 2 sigma interval into a tabular form. It's available on RSP now, and there's a tutorial in the official RSP tutorial section about accessing with LSDB, and you can find the Photo Z in one of the sections in that notebook. But realistically, it's really, really simple. It's just import LSDB and then open catalog with this address. We'll make a best effort to make the Redshift PDF available during the full DP2 release. The reason that is not available now is because of the insanely large file size for PDF, and we're still looking into that. For DR1, we plan to provide a subset of the Photo Z point estimate in the object table, which is automatically joined with the object table, and we will work closely with DM on that. And we're currently working on the live documentation, as Julia mentioned, in RTN 124 about all of these efforts. And thank you. I'll take questions.
Thank you. Can you go to slide 13? With your Photo Z, spec Z plot. So I'm the outlier structure looks different between the different Photo Z estimators. I'm curious whether those outliers are common between the different estimators, that it's the same objects fail in all 6 of them, or if there's some way to combine data from multiple of the estimators to somehow be better than any one of them by itself.
Yeah, I think we've looked into the outlier population, and I would say the answer is they're mostly the. I think they can hear me. Yeah, on Zoom. They're mostly the same sets of objects, but where they're placed in the outlier space are different from different algorithms, because most of them are sort of the extrapolating sample for a machine learning model, and how every model extrapolate are vastly different. So they're placed at different place of the redshift space by different algorithms, but they're mostly faint objects or objects that can have Lyman break or Balmer break solution. So those are the population of outliers. Thank you.
Thank you. So related to this question, so for those outliers, is there any feature in a PDF, like a bimodal feature?
Yes. If you look at the PDF of those objects, they're usually with multi peaks. So also objects with disagreeing, point estimates. The mean and the median, the best will usually be different.
Okay, so there might be some way to plug those.
Yeah. Oh, yeah. And there's a quick.
While we're on this slide, can you just comment on how this group of 6 methods relates to the methods that were used in the stage 3 surveys of kids, HSC, PES, and how the Rubin Photometric Redshifts is building on that experience and reusing algorithms?
Yeah. So the question is, how does these relate to stage 3 algorithms? So the rail is really built by the whole PhotoZ community, and a lot of them are coming from the background of stage 3. For example, DNF is an algorithm I think developed in DES. FlexiBoost is currently used for HSC final year analysis. So it's really a mix of the long-standing Rubin community and contribution from stage 3 surveys. Set of algorithms here. I think BPZ is also heavily used in DES. So a lot of these have roots from previous surveys.
That was a softball question to just get the information out. A harder question is, I think many of these, if not all of these methods, depend on prior information in the training of the method. How do you foresee users accounting for that prior information when using photometric redshifts in their downstream time? How do you see it? How do you see them getting the information they need in order to be able to do that correctly?
Yeah, so I agree with the statement that this is, the PhotoZ method result strongly depends on what you use as a training set, and that's why we put a lot of thought into how we downsample or resample the training set to better reflect the LSSC sample. The goal of the science unit production team is to provide a general purpose PhotoZ that works for most of the galaxies. I will admit, if you are interested in particular kind of galaxy, there might be a better training set or configuration for your PhotoZ that works better, and that's exactly what the value of Linea's work and the Rail open source code is that you can get the training set, you can reconfigure it from our default settings, and you can rerun. If you choose a fast algorithm and run on the subset, it's not going to take you a day, maybe a few hours on the big node. But all of these are open source and open data, and we try to provide as much documentation as possible to support the community for rerunning PhotoZ that might be better for their case.
I think we're also going to try and develop some flags, just for quality flags for rough. I think we're also aiming to develop some quality flags that go with the data. I mean, we can tag things like the outliers and also just whether they have representative metadata or not. And there's a couple of machine learning based ones that we already have coded up to give users who may not be as familiar with the nitty gritty some idea of, is this sensible or is this complete junk? And again, the problem with power law number counts and Ruben going fainter than any survey ever is that the majority of our galaxies are going to be junk. They'll have a terrible book. I mean, at like 27th magnitude, the ones that are one sigma detected in an event, not the ones we're showing here, but the little faint things that are barely detected, which is the bulk of our object. And so having those flagged as this is not very reliable is something that is done.
I think for the interest of time, we should move on to the next talk. Thank you. And
hi.
Yeah. Jose, do you want to share slides or should I switch slides for you?
Whether you change the slides.
Okay.
So, hi, I'm gonna talk to you a little bit about the PC data challenge that we are currently having in the desk Photo-C working group. So, yes, next slide, please. So, yeah, the objective of this data challenge is that people submit their algorithms. So to produce some photometric redshifts using catalog data that is produced from two simulations, flagship and cardinal. And we are providing different scenarios that we call task sets. There are 4 task sets that go from the more idealized to the more realistic. And there is the web page if you want to check the data challenge. Still, if you want to participate, you can do it. Next, please. So the way that we prepare the data coming from the two catalog that comes from the simulations is that we reduce the catalogs, apply some reddening, and then some photometric errors depending on the scenarios. We choose 12 scenarios, LSST year 1 and year 10, and also provide some Raman measurements. And also we do some spectroscopic selections to mimic a few spectroscopic catalogs. And then we give the users a training catalog that contains the redshifts and the magnitudes, and a test catalog that only contains the magnitudes. And we keep a reserved catalog so that we can test the submissions by ourselves. Next, please. So the photometric errors that we implemented mainly come from signal fluctuations, which means that the error increase for the fainter objects. The magnitude error will be larger, and then the signal to noise will be lower for those fainter objects. Next, please. And also we apply some spectroscopic selection that includes selection functions that not all the objects have a spectra, and also a success function, meaning that none of the objects with in a spectroscopic survey are targets. Not all of them have a redshift. So what this implies is that the training set will not be representative of the full data set, and the different algorithms need to take that into account. Next, please. So, as I told you, there are 4 different task sets. The first 2 of them were due 2 weeks ago, but we are still receiving submissions because we haven't started writing the paper. So if you want, you can still submit it. For the first task set, the training set is representative of the data, so there's no spectroscopic selection. The second task set includes the spectroscopic selection, so the training set is not representative of the data. The third task set includes also some narrowband photosieves, which means that the training set includes some fainter galaxies, but the redshifts are not necessarily correct. And the fourth task set includes some recognized blends for galaxies that are too close together in the sky. Next, please. So in each of the task sets, we ask the users to provide a per object probability distribution of the redshift and also a point estimate. We also ask them to provide a Python function so that we can run the estimates on the reserved catalog that we have, and also another function that is able to do both the training and the estimation, so that we can test the estimation time all in the same all the algorithms in the same computer. Next, please. The submissions, we evaluate some performance metrics for each of them. There are two types of metrics. One's like in the left-hand side that only computes the point estimate quality, like outlier rate, the mean of the bias, and the root mean square of the bias. And on the right-hand side, we have some performance metrics that compute also properties of the full P of C. For example, if they are well calibrated, if the errors are correctly, if they are not like too large or too small. Next, please. And with all these metrics, we assign some values that are the objective values, and if the submissions have score these values, we give them 3 points, and to 1 or 0 if they don't get to those values. For example, here I'm showing you, like, we have around 20 submissions already, and this plot shows the root mean square of the bias. The values that we want is the darker shade of gray, and we see that for the task set 1, most or a lot of the submissions behave very good. But for the task set 2, that are the ones on the top, none of them actually reaches the value that we want for this metric. Next, please. So the results of all the submissions are in this page. You can check them in more detail. As I told you, we have around 20 submissions, and although it says that the task sets 1 and 2 are supposed to be already submitted, we are still accepting new submissions if you want. Next. Yes. So here I'm showing you the top 3 entries according to the task set number 2. What we did is that we divided the scores by the largest possible points. So for example, if you see the numbers for the task set 1, you see some ones. That means that those algorithms were able to achieve the metrics, all of them. But in the task set 2, none of them were able to achieve all the metrics. But some of them, if the values of 0.87, for example, or 86, means that they achieve most of the metrics, just not all of them. Next, please. Yeah, here I'm just showing you some of the other metrics. This is the bias of the mean. In all of them, we see the same behavior, that for the task set number 1, the submissions behave better than for the task set number 2. Also, some of the dots are circles, some are diamonds, and this is depending on if the submission is a template fitting algorithm or a machine learning algorithm. And also some of them use data augmentation to have a more representative training set. And we see that some of them do very good, not all of them. Next, please. We have the outlier rates. We see that actually those are much worse. Most of the algorithms don't achieve the value of the metric that we wanted for task set number 2. Next, please. This one is one of those that I was telling you that assesses if the full POC is behaving correctly. For this, actually, most of a lot of the submissions are behaving pretty well for both task sets. So it means that they are estimating the error correctly. They are not overestimating or underestimating the errors. Next, please. This is the estimation time. We want the estimation time to be around 1 millisecond per object or smaller, because otherwise, once we have the full data sets of LSST year 10, we're gonna run into problems. So the ones that have more than 1 millisecond per object will be hard to run at scale. Still, it will be interesting to check if some of those could be improved, because actually some of them, like Lefer or Conclave, that are kind of slow, they were doing pretty well in all the other metrics. So maybe it could be interesting to see how to improve the execution times. Next. The things that we have learned so far, one thing is that a lot of algorithms did pretty well on the representative training data, but none of them meet all the requirements for non-representative training data, although some of the algorithms did kind of pretty well. Also, two algorithms, VPC and Lefer, are template fitting algorithms, and they used flagship simulation to create their templates. So they kind of have an unfair advantage because we are using the same simulation to compare. Luckily for us, we also have the other simulation that is cardinal, so we still can do some more fair comparisons. Other thing that we noted is that one of the algorithms that uses augmentation, that is the NN augmentation, isn't doing very good in the metrics, and we believe that this might be because the simulation that it uses to create the augmentation data is deep sky, and this is different from the simulations that we are using for the data set. So this is something very interesting to note. And other thing is that 3 of the top 5 algorithms, TPC colors, curvature, LSSTV3, and SYN-CS, were actually pretty standard machine learning algorithms. They only do some smart things like adding additional training features like curvature and adding some empirical data augmentation. Next, please. So about agentic AI, agentic AI actually is very useful, for example, to help the submissions that the format of the submission is the one that we want, things like that. But once we try to use it to actually create an algorithm and do everything, none of them were running really well. Actually, some of them were problematic. Like one of them was trying to copy one of the submissions that was already in place. So at least for that, we think that those algorithms still need some kind of human supervision. But well, still we don't know what will happen in tasks number 3 and 4. So maybe they can have better behavior. Next, please. So yes, the last one. Those are the 5 top submissions. 2 of them VPC and Lefera template fitting, and the other 3 are machine learning algorithms. As I told you, LSSTV3 and TPC colors uses curvature, that is the difference between 2 adjacent colors, and apparently this makes them much better. And also one of them uses some empirical data augmentation. So data augmentation using the training data, not using other simulations. And none of them were using agentic AI, and 2 of them were submitted by our colleague Sam Smith. Yeah, so that's all that we have.
Any questions for Jose? I guess Sam is still a better agent in 2026 on Photometric. What we learned so far. There's no question in the room. I'll quickly check. Yeah.
So what can be done about Lafar? It's interesting that it did so well in the challenge, but couldn't be run on BP2 for being too slow. So what's the outlook there?
I'm not sure. Jose, you want to take that? I can answer it.
Maybe can you answer?
So there are mainly 2 approaches for speeding up the bar. The first one would be you can generate the redshift color space from the template and then basically emulate those generations. Because basically what LaFar does is it goes through all the templates, it generates color for them, find the best likelihood for a given measure. So being that process would speed it up. There's another effort of putting LaFar in GPU, and that should hopefully also speed up. And we've already had some good preliminary speed up on the order of 100 times from Leo in the rail, which is very promising.
So for the so for the property, are you using the option ATM or not?
I didn't make the bar submission.
I don't remember. I think it's turned on, but we'll have to double check the parameter file for sure. Actually, come to think, I doubt we did because unfortunately we know in these simulations that they don't include AGN, so it actually artificially penalize it against the others because we give it more freedom than the simulation. So for the data challenge, I think we probably do not have the AGN turned on. For DP2, we probably ran it with turned on.
So it means that if you turn on, it can be even a bit slower, right? But more proper. Thank you.
So I'm not from the Redshift work, but in the bank of investigation, we're looking at the data, then there's more like not really a real method. You don't have to real data to make any conclusions.
Are you asking for classification?
No, because it's regression. Yeah.
Yeah, so it is a problem for template fitting because the template is used to simulate the data. So for machine learning, we do make sure that the training set is a mock of the spectroscopic selected training set in the real world. So I think there was a slide here that basically articulate how we generate the training set by putting photometric noise and spectroscopic selection. And the algorithm can only use those. Yeah.
The redshift
If there's no more question, let's give Josue another hand.
No, this is just
The slide.
Okay, great. So I'm going to talk a bit about the NFZ side of the data challenge we've been developing within Desk, as well as some comments on sort of spectroscopy and what we need to achieve our PhotoZ goals in general in terms of gathering more spectra. So this has been work going on primarily in Desk. This is my first Rubin community workshop, though, so some of this may sound very Desk-centric, but I'm hopeful that it just starts a conversation that's helpful for the entire community. And presenting on behalf of many contributors who've been helping make this happen. So I know that we may come from a variety of backgrounds. I want to just comment on sort of why photometric redshift distributions matter in the context of lensing specifically, and sort of constraints on dark energy from galaxy lensing. And so this image is meant to sort of cartoonishly sort of illustrate that. What we're seeing here is the source plane with the Vera Rubin logo at various redshifts in a dark matter only simulation. And you can see that depending on the source plane, depending on what redshift it's at, right, the amount of distortion you see varies. one, from purely sort of geometric reasons, the lensing kernel is changing, but also because the actual large scale structure that it's passing through, the light is passing through from the source plane is changing. So in order to interpret the distortions that we observe that look like this, in order to interpret the lensing signals, we need to have some sense of the redshifts that the lenses and sources are at. So the goals of the N of Z side of the data challenger, first, just to test technical readiness of our inference pipelines, where we know the truth. A second, to create a set of simulations that will ease the process for people to develop improved and new methods, right? So we're hoping to sort of unlock people's creativity by creating a nice sandbox for people to develop new methods on. And then we can, compare methods with uniform inputs and outputs, right? The input simulations are the same, the output formats are the same, so it's easier to compare the methods. The motivation here is very much, though, that the uncertainty on mean redshift of lensing source galaxies in precursor surveys to LSST exceed desk targets. So here, the x-axis is mean redshift for broad tomographic bins of lensing source galaxy samples, and the y-axis is uncertainty on that mean redshift. The gray are science requirements set out by the Dark Energy Science Collaboration for years 1 and 10, respectively. And the color bars are various precursor surveys. And so they're in excess of those targets, generally speaking. And in particular, as you go to high redshift, things become especially challenging. So the NMC data challenge in a nutshell, what are the inputs and outputs? We have mock wide fast deep. We have a mock wide fast deep galaxy catalog with LSST bands, and as well as specific deep drilling field catalogs with overlapping near infrared data from, in particular, Roman. The outputs, the job in the task is to create tomographic bin assignments, depending on the task set, tomographic bin assignments for the galaxies, and N of Z in those, given those bin assignments. So we have 3 task sets right now as it's currently defined, tracking the P of Z challenge with increasing difficulty. So task set 1 is good. It's a fairly bright sample, so I less than 23. 1 million galaxies sampled uniform randomly from the full sky. And the task here is only to estimate N of Z. The tomographic bin edges are going to be given. 2, we're going deeper. And in addition, and so we're also introducing a wide fast deep and DBF split. In the deep drilling fields, we're introducing Cosmos-like photoz's, where the redshifts are not the truth. So spec here means true redshift simulation. The photoz's will be not the truth, and they're drawn from a distribution which is trained from the data that we see, biases in Cosmos photoz's and spectra in the data. And for the final task set, we're also adding tomographic binning to the job. So our evaluation metrics right now. So we are going to penalize 4 things essentially right now. 1 is bias in the mean of estimated N of Z relative to truth. And so that's what that first column is showing. And we've kind of categorized performance from sort of reasonable baseline to sort of meeting science requirements as you go from top to bottom there. We're also going to penalize bias in the variance. So a flattening, broadening of the N of Z relative to truth is going to be penalized as well. We're going to penalize uneven bins. The idea being that all else being fixed, you want even signal to noise in your bins, and as well as penalizing unassigned galaxies. So entrants to the challenge do have the choice to throw out certain subsamples and say, you know what, I can't calibrate these, I'm going to exclude those. That's fine. You will be penalized for that though. So it's a trade-off between sort of constraints and assignment. We'll look at sort of reported uncertainty, right? So what an entrance reported uncertainty. But hopefully, so the way I think we should characterize this is it's a strange game. The only winning move is not to play. I think the idea is that if we've designed this well, everyone kind of should lose. And the reason is shown here. So here on the x-axis is I-band magnitude. The y-axis of the left-hand panel is normalized median absolute deviation of the true redshift and the Cosmos-like photoz's. The warm colors, red and orange, are our files that will be distributed for the challenge, and the cool colors, the green and blue, are from Kostovan et al. 2026, where they have a bunch of spectroscopy and they compare these to the Cosmos photoz's. And so what you see here is basically the scatter in the photoz's, right, that we've tried to mock up in the simulations, and it actually kind of inflates because the sample scatter that you observe is in general expected to be lower than the population scatter. The right-hand side panel is just showing the outlier fraction as well. So the calibration data that's available to learn the NFZ at the faint end has these biases baked in, which are, we believe, a priori limiting to redshift calibration. So, so this is an element of realism here that we're that indicates this is going to be hard. This is going to be hard for everyone. And so, commenting on that a little further. Commenting on that a little further, right? If you break down precursor surveys uncertainty into what is due to the method alone under idealized conditions and what is due to calibration data, the full uncertainty is the full sort of like color bar here, but the method alone is the non-dashed portion, really at the bottom here, kind of near the targets. So we do already kind of know that the calibration data limitations are sort of the driving factor in our photo uncertainty for lensing sources. In summary, we're preparing an NFZ data challenge to build a sandbox for methodological improvement. We want to sort of unlock participants' creativity here. Stay tuned for a release of task set 1 in August. We're trailing the PFZ side of things, building on that infrastructure. With that, though, I think that there's a little bit of time for me to comment more on what are the spectroscopic data samples we do need for lensing source redshift distributions moving forward, kind of like longer term, bigger picture. And this is again presenting on behalf of many contributors. In these conversations have been building in DESC, I think, and I want to give a special shout out to Jeff Newman, who's been developing this field of research longer than I've been around in the field. So what do we have now? We have incomplete, non-representative spectroscopy. And so this is showing again from that paper, Kosovan et al., as a function of photo Z on the x-axis and HSC I-band magnitude on the y-axis, spectroscopic completeness, where white is none and this dark blue is full. This is a mixed sample. This also includes AGN here. But what you'll see here is that at sort of like LSST depth, the coverage really just drops off really dramatically. And so this is a limitation for our science. And so what this means is that at the faint end, we rely on Cosmos PhotoZs for direct redshift calibration. Here's an analysis by a grad student at Princeton, Azana Queen, where in the 4 tomographic bins of the HSC year 3 analysis that's shown in the bottom 4 panels here, you're looking at what are the calibration redshifts that are being used in order to infer NFZ. And the Cosmos 2020 PhotoZs is this blue color, which you see dominates at the faint end across all the bins. Now, recent observations from DESI contribute tremendously in the Cosmos field, so there is progress being made, but you can see that it's dominated by Cosmos Photo. And so will that work for LST science goals? I think the basic answer is no. Relying on Cosmos PhotoZs for direct calibration is the dominant uncertainty for PhotoZs in general for lensing science. So here's an illustration of that from the DES Year 6 redshift calibration led by Boyan Yin. The total uncertainty, this is variance on mean redshift, is shown with the vertical axis, and the 4 tomographic bins are shown on the x-axis here. And obviously what sort of is visually salient here is the red, right? The redshift sample here. What this is doing is sampling the distribution of biases that's observed in Cosmos PhotoZs and sort of just adding those biases to what we have and just resampling that and re-inferring the NFZ and getting a different mean redshift every time. And so what you see is that blows up far in excess of the LSST elements. So what we really want is, fainter spectroscopy. And so one important aspect of how to achieve this is by using DESI in the equatorial deep drilling fields, the equatorial Rubin deep drilling fields, Cosmos and XMM. So getting samples down to I of 25.3, roughly 20,000 to 30,000 objects, and covering 2 deep drilling fields, not just 1, in order to get the sample variance in that sample down to requirements. And so we've been trying to just organize the resources available and how we might be able to take advantage of them to achieve DESC's science goals long term. And so I think we can call this something like an all of the above approach. So there are 4 elements here I think are really important. One is proposing an intercollaboration agreement to take advantage of Foremost spectroscopy. There's a program within Foremost. This is the 4 meter, I don't know what the O is, but 4 meter O and then spectroscopic telescope. And they have a program called 4C3R2, which has been targeting specific, in this case, SOM cells, as you've seen earlier today, SOM cells where we don't have spectra. And it'd be great to get an intercollaboration agreement to get access to those for DESK. Also, there's a Subaru PFS in kind with the Japanese community, which allows for Subaru telescope time for US researchers broadly, as well as fiber filler programs, right? Spare fiber filler programs. And so we're trying to develop proposals for those different kinds of time, right? So applying for US time generally to go faint, but also just filling spare fibers with sort of a more diverse sample. And there are precursor, there's proposals that have been led like by Jeff Newman, Deepertube Day, Jamie McCullough et al., and that we're basically trying to refine and resubmit. And as well as defining potential target lists for deep DESI observations in the equatorial and deep drilling fields of Cabo and XMM. And finally, targeting failures from the above with VLT moves.
So when you say failure,
yes,
does it mean that galaxy doesn't have enough strong emission line to do the depth?
For example, yeah. For example, yes. Thanks for bringing that up. Yeah, when I say targeting failures, I mean when an element higher in this list observed something and was not able to secure a successful redshift, targeting it again with a different resource.
Because the VLT months is a super instrument.
Right.
Yeah.
Right.
Okay. Good. You want to make sure that the failure is a galaxy that will be observed. How do you do that?
Sorry, I don't understand the question now.
So if you don't have the redshift, you want to make sure that is a target for the VLT, for a very large telescope.
Correct. Yeah.
So it should be something you have to make sure cannot be observed with anything else.
Yes, that's right.
Yeah.
Yes.
Okay. So you just.
Yes.
Yeah.
Yeah, I'm going to repeat the question in case I don't know if the audio is great for on Zoom. The question is sort of like, what does failure mean in this context? And VLT is sort of a very powerful instrument, and so would we be reserving that for objects which for which we don't have successful redshifts and can't get them with the other instruments? The answer is basically yes.
Okay, for which you are sure that they are either redshift or anything.
Yeah.
Yeah.
And so that's pretty much all I had to say. So summary, what we currently have is non-representative spectroscopy supplemented with complete multi-band photos in the cosmos field. What we would ideally like to have is magnitude-limited spectroscopic samples with LSST depth. And our path to getting all this is kind of an all-of-above approach, using many different resources that have different strengths and weaknesses and available time. That's all I have to say. Mike.
Yeah. How do you select the factors? How do you know that you will obtain the redshift matrix?
The question. Oh, you heard the question. We cannot guarantee a priori that we would get a successful redshift in any case before having it, but we cannot guarantee that. We would select failures from the prior programs where no successful redshift is observed. There's no sort of observed strong spectral features, but we might expect maybe it's shifted into the near infrared, for example. Yeah, but this we don't have a well-defined failure set yet. Fair enough.
So I have a question about the PFS time. So as you may know, there's also a Roman Subaru time.
Yeah.
And then so we actually submitted the proposal with Jeff. Submitted the proposal recently. So I know that some cells are different because the Romans are more like near infrared data. But I guess that there should be some coordination between LSST and the Roman. Possible. Well, one thing I should note is that the Roman Subaru data, there is no proprietary field.
So the question is generally sort of coordinating Roman. So yes, so Jeff Newman has been leading this essentially, right? So Jeff Newman has a proposed program, super, and definitely agree there should be coordination. In particular, I would love to know talk more about the status of the near-infrared arm on PFS in order to optimize the time that I've seen. So we should definitely talk more and move Jeff into that.
You have a question on Zoom.
There's a question on Zoom.
Dan, please speak up.
Yeah, so I've asked a variety of people how much coordination there is ongoing between these various spectroscopic surveys, especially in the deep fields like Cosmos and XMM. And the short answer I got is not much or not enough. Is that a problem? Should there be more? Is it good if you just get, 4 redshifts from 4 different instruments of the same galaxies in Cosmos? Or
Yeah, I think no. And so that's part of why I made this slide, essentially, right? At the very minimum, we want to avoid duplication. We don't want to observe the same galaxies that Foremost has already observed, specifically to target the kinds of lensing source galaxies where we don't have a good spectroscopy. And so we very much want to help start that coordination. In DESC, we are exploring the possibility of a topical team within the PhotoZ working group to achieve this goal. This slide is very much inspired by that exact problem, but I would say that it's very early stages. There were hands, but I can't remember.
So when there's when there is more abundant spectroscopic data, would we still need to use synthetic source injection as part of the mapping from the deep drilling fields to the wide area?
Yeah, that's a great question. So the question is when. So the question is, if you've learned the color redshift relation really well, in optical plus near infrared deep field space, can you calibrate N of Z? Do you still require learning the probabilistic mapping between deep and wide field photometry with synthetic source injection? And the answer is, I believe, yes, because these are independent contributors to the total uncertainty on the lensing source sample redshift distributions. One is sort of your uncertainty on the color redshift relation itself, and then the other is the mapping between the colors that relationship is learned in and the colors of your lensing source sample. I view those as ultimately as combined uncertainties to your NSE. So the answer is yes. We have the infrastructure to do that, it's just a matter of the compute expense, right? And human time.
I think this is a question for Julia. But with the PZ server, it seems like that could have a role to play in helping this coordination. If I'm optimistically expecting all of these spectra to eventually end up in Brazil for the benefit of everyone in the LSST science community, have you thought a bit about how you could also be helping now with the coordination, like getting some of these PFS samples going, or starting to build up lists of targets that have been proposed, even though they don't have spectra yet, just to avoid this duplication? Just wondering if you've thought much about this.
Not at this level, but yeah, we are definitely interested in participating that actively and help as much as we can. I'm also participating in Roma Photometric Redshift working group meetings. So, and I also asked about also sharing these public spectroscopic compilations that we are doing here with them. So as an exchange, scientific exchange between the two projects. Yeah.
Yeah, so we're at time.
Let's thank Justin again. And we're at time. Thanks everyone for participating. We'll close the session. Have a good weekend.